Okay, one thing I forgot to mention, reducing agent causes reduction to happen. Okay, it gets oxidized. Okay. And conversely, an oxidizing agent causes oxidation to occur. It gets reduced. Okay, so in the last example that we used, the chromium was being, the dichromate ion was getting reduced. So this is the oxidizing agent. Conversely, the SO3 sulfite ion was being oxidized. So the sulfite ion is the reducing agent. Okay, you may be asked to draw a simple voltaic cell. A voltaic cell, remember, is spontaneous. So remember that your E of your cell is negative. Okay. Thing that I remember about voltaic cells which helps me is I remember red cat and N-ox. This reminds me that reduction happens at the cathode, and that is true for even electrolytic cell. N-ox is oxidation happens at the anode. Okay. For a voltaic cell, the cathode is positive and the anode is negative. This is the part that switches for an electrolytic. Okay. This is always the case, no matter what the cell. Okay, so sometimes you'll be asked to draw a voltaic cell. You should be able to sketch a voltaic cell. Hopefully you can spell it correctly. You want to draw the two half reaction vessels. You want to make sure that your anode goes into the solution. This is a voltmeter. And don't forget to put the salt bridge so that it is within the solution. Right? Say in this half cell you have solid zinc going to zinc plus 2 aqueous plus 2 electrons. Since it is losing, this is oxidation. That means that this is your anode. It will be negative. In solution here you will have zinc ions. And say that this is the reduction. That means that this will be it'll be the cathode with copper ions there. This will be plus. Electrons are going to flow towards the cathode. Anions will be flowing this way. Typically it's something like nitrate. Cations flowing this way. You may want to label that the cathode is probably made of copper, the anode is made of zinc. Over time, this is going to go away. Okay, and then you will see copper build up here. All right. Things to watch out for. For aqueous solutions, remember that in solution you have these ions which might reduce or oxidize before your actual other ions that happen to be in the solution. You want to look at your data table to keep that straight. Okay, differences in a electrolytic cell. One, you're going to have them typically in the same solution with a battery. Or power supply. The electrons flowing from here. This would be your negative electrode, which is the cathode in an electrolytic cell. Reduction is still going to take place there. Your positive is going to be your anode, and you're still going to have oxidation there. Say we have molten here. Reduction then will be my sodium ion. Remember, it's molten, so it's going to be liquid going to my sodium metal. Shouldn't have wrote it in my cell, but I couldn't fit it. And then at the anode, we will have the chloride ion making chlorine gas and 2 electrons. Okay, I think I'm going to stop there. No, let's do one more because this is going to be factors affecting discharge of ions. During electrolysis. You're going to have to look at the position in the electrochemical series. Okay, and again, that's you're looking at water. Is water going to be reduced or oxidized in preference to, say, sodium? The answer there is yes. Okay. 2, concentration is going to affect. And we'll see this with sodium chloride solutions. For a concentrated solution, we're going to see chlorine. Okay. For a sodium chloride dilute solution, you're going to see mainly oxygen produced. In reality, you'll see a mixture, but depending on it, you're going to see more chlorine for a concentrated solution and then more oxygen for a dilute solution. The nature of the electrode is also going to matter. Okay, you know, the difference between inert versus, say, copper. Spell copper right. If you use inert and you're plating out copper, once you use all the stuff in the solution, you can't. It's going to stop because you used it all. Okay, that will end this screencast.